Good afternoon, everybody. First of all, I want to thank Dr. Liang Ming for inviting me to give this talk for your Smart Grid seminar at the Precourt Institute for Energy at Stanford. And I'm very honored to be a guest speaker here. I also want to thank Chen Wu and Wahila to provide the logistic support to my seminar and Chen Wu's introduction. The title of my presentation is Current Large-Scale Testbed, LTB, as a virtual power grid for closed-loop controls in research and testing. This testbed is commonly known as the current testbed, LTB, in the rest of this presentation and in the research community in electrical power system. This work of current LTB is not possible without the funding support from Current, which I will mention a little bit more details later on. Current LTB is a big project by a great project team. I'm very grateful to our team with several main contributors as follows. The first one is Dr. Kevin Tomasovic, who co-leads the current LTB project and is also the current overall director. Kevin initiated the idea of developing current LTB back to 2015 and then asked me to drive this work. I'm also grateful for his trust of me to lead the effort. Also, I want to thank Dr. Hantao Cui, who is the chief technologist for this effort. Hantao is my former PhD student and now the research assistant professor at Current. And he is a very brilliant young man and will be an assistant professor, tenure track assistant professor at Oklahoma State University starting this fall semester. Also, I want to thank Dr. Joe Chaw and Ali Abu as senior technical advisors for Current LTB, and certainly many other faculty members and graduate students within Current contribute to the work as well. I'm really, really fortunate to work with all of them on this Current LTB project. Okay, next I want to borrow a minute to briefly talk about my department and my university. My school is University of Tennessee at Knoxville as UT or UTK. It was established in 1794, even 4 years before the establishment of the state of Tennessee. So we have a really long history. We are best known to general public for our magnificent stadium, which can hold more than 100,000 people. So it's our landmark. If you have a chance to visit us here in the future, I will definitely show you around our campus and this huge building, huge stadium. Our department of EECS is located in the new Minkow building, opened in 2012. We have about 50 faculty members with 4 US NAE members and 10 plus IEEE fellows. In the power area, we have 5 professors in power system and 5 in power electronics. And the department is the host of and the headquarter of Current Research Center. Okay, our EECS department current existing undergrad student enrollment reached about 800, and we have 170 PhD students. Our research expenditure per faculty reached more than $500,000 as of fiscal year 19. Okay, so we're ranked pretty high in some measures in terms of PhD students per faculty members and research expenditure per faculty members. Okay, all right. So now let's talk about current, C-U-R-E-N-T, this is single R, okay. So it stands for Center for Ultra-Wide Area Resilient Electric Energy Transmission Networks. See, like I mentioned, oh, excuse me, it's a single R. You know, university engineering professors couldn't do spelling very well. So when we realized we missed 1 R, then that's too late. Okay, so now we try avoid to talk about the current versus currently, okay? All right, anyway, CURENT is funded by US National Science Foundation, the Engineering Research Center program, and its funding comes from both US NSF and Department of Energy. Excuse me. The lead university of CURENT Research Center is University of Tennessee with 3 partner schools, RPI, Northeastern, and Tuskegee. Our base budget is $4 million per year from 2011 to 2021. Yes, this is the 10th and the final year of CURENT. It's the first and, excuse me, the first and only NSF ERC dedicated to bulk power system research. And we have more than 30 industrial members. Okay, here's some introduction of current vision. It is to develop control and modeling approaches for a nationwide grid, which is fully monitored and dynamically controlled for high efficiency, high reliability, low cost, better accommodation of renewable sources, and full utilization of storage and responsive load. Also, from the educational side, our mission is to produce new generation of electric power and energy system engineering leaders with a global perspective coming from diverse background. Here is an overview of the systems. The current research scheme includes 3 planes: fundamental knowledge, enabling technology, and engineered systems. And they interact with 4 different research threads: monitoring, modeling, control, and actuation. Here, the engineered systems basically includes hardware testbed, or HTB, that's another testbed, and large-scale testbed, which is software-based. Testbeds will drive the center's research program via system specifications and closed-loop scenario studies. Background: why current LTB, or why we want to build this large-scale testbed? The researchers in power system community often struggle to obtain realistic data for research, since we don't really own or operate any power grid. Also, researchers like us need to use multiple tools to manually create interactions among different software packages to achieve our research goals. For instance, if someone wants to test a real-time control algorithm, he or she needs to use a dynamic simulation tool to produce mock measurement signals that will be fed to another piece of software as control inputs. And then the output from such a control module will be fed back to dynamic simulator to verify the control algorithm. During this process, either a manual or some scripts need to be developed to facilitate the closed loop interaction. So our goal is to make this process automate. So then the user can make one button click or maybe a few button clicks to finish the closed loop interaction. Okay, here the closed loop automated interaction is really the key. Okay, this differs this large scale testbed from typical simulation tools. Okay. Meanwhile, we also want some standardized models and test systems with high penetration renewables for easy benchmark among different research results. So in short, LTB is closed loop simulation platform plus large scale system models. This slide shows the overall architecture of LTB modules. On the top, we have the current models with HVDC overlays, as well as wind scenarios for our research. On the bottom, we have modules representing conventional EMS functions such as state estimators, dispatch, and visualization modules. Okay. On the left, we have possible simulation engines for power system dynamic studies, such as our in-house Andes tool, or OpenRT's EFISM, GridDyn's Lawrence Livermore National Labs GridDyn tool, or other customized modules. Okay, on the right, we have this new research algorithm and controls, which represent the research results from the users of this LTB. All these 4 blocks are connected by data streaming and communication network module, which I will elaborate later on. Here are some design considerations, such as interoperability with a modular architecture. Also, we want to consider measurement-based control interactions to simulate PMU sampling and streaming. We also need large-scale models, such as 1,000-bus North American power grid model with projected HVDC overlays. Here, I want to talk a few words about the grid simulation engine. Right now, we have our own in-house Python-based tool called Andes, which has a built-in library for fast prototyping and so on. So Andes is like a white box to us, so we can do whatever we want for fast prototyping of modules and routines. And also we have interface to other research tools like GridDyn, developed in C++ with features like a connection with Modelica and high performance computing. Also, we interface with commercial tools like OpenRT, EFISM, which supports Modelica, Python interface, and so on. Our goal is to use our own white box Python-based engine Andes for fast prototyping in a relatively smaller system, like a few hundred bus to 1,000 bus. Then once verified, we can utilize more commercial grid tools for much larger scale verification in the scale of tens of thousands of buses. Here, I wanna talk a bit more about our in-house tool called Andes. Available functions include power flow for AC-DC hybrid system, time domain integration, eigen analysis, and some plotting data streaming interface. We also have unique features like symbolic modeling. And for available models, we have 49 models included, such as general, gen class, and PV models, and wind turbine models. And we support several data formats like our own Andes data format or PSSE and MATLAB format. Supported test system include MPCC 39 and 1 to 140 bus system, and also WECC, EI, and ERCOT system with 50% wind and 30% PV models. Open source distribution can be found here. In the past couple of years, we developed a hybrid symbolic numerical framework to enhance and improve the previous dynamic simulation engine of Andes, or this is basically the new generation of Andes. Okay, symbolic programming basically means that writing code for complex mathematical equations is just like typing an equation in Word. Okay, once you follow the symbolic modeling language, then we have code generation which will generate the code such as solving power flow, solving Jacobian, solving numerical integration for power system dynamics. So in other words, once you type the equations, then the symbolic library will generate the code, Python code for the programmer or the user of this tool. This significantly reduces the effort of researchers so they can focus more on research works on their own rather than spending a lot of time in coding and debugging. Certainly, we also need traditional numerical programming in the loop for some maybe customized functions. This is shown in the blue blocks here. Okay, this the yellowish block represents the symbolic programming part. Okay, so this is that's why this approach is called a hybrid symbolic numerical framework. As the engine is really the critical part in this platform, we made a lot of verifications for our simulation engine. Here, it shows our benchmark with MPCC 140 bus system using TSAT, which is a commercial tool for power system dynamics. Okay. As shown in these two diagrams, the dynamic simulation results match very well with the commercial, with results from commercial tools like TSAT. The left diagram shows the frequency at bus 22 and 25. Well, we're supposed to have 4 curves, okay? But we seemingly have only 2 curves here. The reason is that the 2 curves from Andes and TSAT match with each other very well. So they fully overlapped. And so then that's why it looks like only 2 curves here, but actually there are 4. The same results can be observed for the right diagram for the terminal voltage at bus 21 and 25. Next, I wanna talk about the LTBPMU module, okay. This slide shows the measurement model built-in LTB called LTBPMU. After the simulation engine performs the dynamic simulation, the ideal results will be processed in the following 4 steps. First, we added a delayed model. Then we added some measurement noise into the data. And then we may consider loss of data at some probability. Then we obtain the realistic data or non-ideal measurement data. So then we can send this non-ideal realistic measurement data to other modules like communication module or other modules for further processing. So this slide shows the LTBVis, which is a web-based visualization. For power system researchers, the visualization tool helped us test our research code and identify problems or even motivate us to find new research ideas. Later on, I will show a few short videos which you will get a better idea of the visualization tool. We also developed several system models and various wind scenarios. We start with NREL's National Renewable Energy Laboratories wind speed data for future wind farm locations and wind dynamic modeling guidelines. Eventually, we built the 50% wind penetration in WECC and 50% in ERCOT and 50% in EI for wind, and as well as 30% solar penetration on top of that as future scenarios. certainly we build many other scenarios in between 0% penetration to 80% renewable penetration. All these three systems are integrated together to form what we call the 1000 bus current North American system. We also use the MISO, Midwest and Mid-Continental ISO study results of the multi-terminal HVDC topology as shown in the figure here. Next, I want to talk about the data streaming part for the LTB. We basically have two approaches. The first is the DIME. DIME stands for Distributed Message Environment for passing data between asynchronous heterogeneous modules. It is a point-to-point data streaming approach for fast prototyping. For example, if one module wants to send something to another module, so like a LTB PMU may want to send something to realization, then this can be done with DIME module. And also we have LTBNet. In LTBNet, we employed a tool called the MiniNet to develop the communication network details for LTB. It's based on standard IP-based streaming or detailed communication network. Next, I want to discuss a little bit about the DIME. It is a Python-based transparent streaming server, and it supports unlimited MATLAB or Python or C++ clients. Developers can import DIME API and then gain a streaming capability. In this diagram, here we show LTBVis here on the left, and then the OpenPDC on the right, and the other modules on the here, and that's the Andes and the other modules here. So as long as you follow the streaming protocol, and the streaming server will help delivering data from one to another. LTBNet. This is the emulation of communication network. In the last few years, we completed the software-defined communication network emulation, which is now integrated in the loop of LTB. From the viewpoint of module dependence, we have a 4-layer architecture with a physical power system layer at the bottom, and then measurement layer, communication layer, and the application layer like EMS functions or control functions, okay? About the communication topology, we constructed a nationwide communication network. I wanna mention that there's really no publicly available model about a nationwide backbone communication system. So we use this ACM report here to develop our US communication network and use it to emulate the communication system in the current grid. So now we can bring all the pieces together to form the data flow diagram in LTB, okay? We start with the large-scale system model and high penetration scenarios. Both are fed to Andes, and then the dynamic simulation results or the data output will be fed to LTBPMU through DIME streaming server. Okay, at LTBPMU, we create realistic non-idea measurement data from the idea data, basically by embedding noise, embedding some communication delays or missing signals. So then what we get here is realistic measurement data. And that measurement data will be forward to different modules such as OpenPTC for storing the data, and or LTB visualization to visualize the system. And also it can be forwarded to the new control algorithm. That's basically the researchers' results. And then in this new control algorithm, based on the research, maybe some parameters will be modified. So then that modified parameters will be sent back all the way through DIME server back to Andes. So then the Andes will make adjustment in its dynamic simulation, just like in reality, the control signal being taken and actions being taken. So then that will make the system perform differently. So then the new updated dynamic simulation results will be sent to LTBPMU, and then here there's some processing to generate non-ideal realistic measurement data, and then we repeat this loop. So everything happens within this loop and happens in real time. So that's why we call this a closed loop simulation. This is really the fundamental difference of this platform from maybe it's a simulation tool. Okay, for a typical simulation tool, it is open loop, but here it is closed loop. So also I want to mention this new control algorithm is based on researchers' results. So we basically provide this platform as an environment for the researchers. So then they can focus on their research work rather than dealing with all the simulations and mock measurement creation. Now let's play a quick demo to illustrate what the LTB can show you with this LTB visualization as a front-end presentation. So left side shows the uncontrolled case, and the right side shows the controlled case for WECC system damping control with wind generators. This case study is a good example showing the LTB platform can demonstrate the advantage of new control algorithms. Also, it helps researchers to identify and view the simulation results. Okay, so after some disturbance, there's a system oscillation, and then this controlled case will bring the system back to steady state a lot quicker than the uncontrolled case. Okay, and also we have a plotting window to show the timeline flows. Okay, you can also see that for the controlled case, the dynamics dies out a lot quicker. So that's why we call this a research demonstration platform. Okay, the actual algorithm about this research can be found in this paper below here. And also I want to mention that it helps the researchers to view and identify problems during research. For example, without this front-end visualization, it is very difficult for someone to find out what's going on or what's going wrong among the enormously large volume of data at hundreds of buses and at the data rate of 20 or 30 snapshots per second. Next, I want to show another quick video of a project that a deliberate cyber attack may cause the system to separate into two islands, which are not necessary. So the blinking dots are the PMUs with malicious bad data injection. The right diagram, this small window here, shows the maliciously injected data causing operator to think the system frequency deviates from the threshold to trigger a special protection scheme of separation. So which means the system is actually good, but because of the false data injection attack, the operator thinks there's something wrong and then started the system separation, which is not necessary. Okay. All right. Yeah. Okay, let's move on. The third and the last very short video demonstrates the impact of communication delay on control. The left part shows the case of no delay, and the right case shows the 300 millisecond delay under denial of service attack, for example. Let me play the video. So after some disturbance happens, the previously working algorithm, assuming no delay, will not work. Okay, you see here. So without delay, when everything communications idea, it works, but with 300 millisecond delay, then the algorithm doesn't work. So this is as an example to demonstrate what the platform can show or can help researchers on their research works. Here's a summary of LTB Achievement. We've finished a number of modules, including Andy's simulation engine, DIME server, LTBPMU module, a number of current test system, LTBNet for communication system emulation, LTB visualization, and also we finished a number of research integration for demonstration. And I'm also pleased to report that current LTB won the 2020 R&D 100 award last year. Here I want to briefly mention LTB as a driver for research. As a platform development, our researchers are main developers. Okay, so and also we have a research-driven development, and then in turn the platform enhances the understanding of the models, methods, and the systems. And we also have large-scale system and scenarios which are used in research case and inspire research works that use data to calibrating our models. Okay. Finally, I want to summarize the difference of traditional simulation studies versus LTB-based approach. In terms of prototyping, traditional approach is more open loop based on MATLAB or Simulink. LTB approach can integrate many different programming languages. Right now we have MATLAB, we have Python and C++ for different modules. Data interface, we have online data streaming between heterogeneous modules, like I mentioned previously, developed maybe in different programming language. And a traditional approach, usually the offline or no automated interface. You have to do it manually. Communication network, typically none in traditional simulators. And we have a built-in LTBNet. For closed loop testing and systemic testing, usually is a manual simulator controller loop. However, in LTB, we have real-time closed loop testing environment, and we have ready-to-use modules. Okay, so this one shows our virtual control room at the current research center located at the first floor of Minkow building in the Department of EECS, University of Tennessee. Here are some ongoing users of LTB. We have 5 software maintenance support agreements signed in the last academic year with users from universities, national labs, as well as industrial users. It also played a critical role in for funding, such as in 6 externally funded projects totaling $4.5 million. And also it's being used in one of LLNL's project. And it also supports a recent NSF career project by one of our faculty members, Dr. Polgar at UT. Here's the roadmap for LTB. As you may see, we have taken consistent progress towards the Gen 3 goal. That's the NSF terminology. So since this is our year 10, so we're basically here. Okay, you can see that this is a progressive effort. We started several years ago from 20% renewable penetration to 50% to 80% regarding the scenario development. And also in terms of LTB platform functionality, we developed a lot of functions over time. And now the LTB is quite a mature tool. Right now it's in the maintenance mode. Some future directions, certainly we need some minor enhancements, such as enhancing load models for large scale system. Right now we have the IP and the motor load model, and maybe we want to enhance it with some demand response model there. We want to refine realization for various use cases. We want to improve the computational efficiency, and some possible larger enhancement may include integration with our hardware testbed, which is a hardware-based test platform. We may link it with economic and market tools, we may link distribution system simulation models to make a co-simulation environment. We are seeking some external grant to a larger grant to develop major modules like this bottom 3 shown here. LTB is available at GitHub. This location is open source, well documented. And the majority of this content can be found in this paper published in IEEE Power and Energy magazine. And also we have several related technical papers shown listed here. And this acknowledgement, we want to thank our funding support from US NSF and the DOE, as well as our project main team members. We want to thank our industrial members that's here. And this is the presentation.